The other more commonly used process now is coulometric methods, where rather than using weighing methods or gravimetry to determine the amount of material, you actually determine the amount of electricity that you pass to do the reaction. Okay, so you're going to record the electricity or the charge typically that you pass. And so you know, for example, from Faraday's law, this relationship between the charge and the number of moles of material, and this n is usually known. Sometimes you have to determine it beforehand, and the Faraday, of course, is a constant. So you can use the relationship between charge to get the number of moles. And you can get the number of moles or charge by integrating the time or the current as a function of time. So you do the reaction for a certain amount of time, you take the total current that passes during that period of time, integrate it, now you've got the charge. So a device used to make that measurement is a coulometer. And you can do this manually. You could have a trace recorded on chart paper, and you can use various methods to take that current trace and integrate it and get the charge. One example would be to cut out a sheet of paper of the same type as the graph paper for a certain amount of area. You can weigh it and get a weight per area, and then you take this trace and cut it out and weigh that, and that's a same sort of indication. You get the amount of area. Area under that current curve would be related to the charge. The way a coulometer works is often it uses a capacitor, and it takes the current that flows in and it uses a capacitor as an integrating element. So the more the voltage increases on a capacitor, the more charge is on that capacitor. So by detecting the voltage across the capacitor, you get a direct readout of the amount of charge that has been passed. The problem with all these methods is it's very tricky to get a good time measurement, and it's also tricky to get a good charge measurement because the charge cannot leak off on or off that capacitor from other methods. And so for small amounts of current, that often is really, really tricky. And actually for large currents, it becomes tricky as well. The other thing with the problem with the coulometric method is that it requires, initially at least, 100% current efficiency. We have to know when we do the reaction that all of the electrons that we're putting in is involved in doing the reaction overall. Because if it's not, we're going to measure the charge for some other side reaction, and that won't tell us how many moles of material that we're interested in. So we either have to know that exactly that it is 100%, or we have to know the conditions to such a degree that we can correct for the non-100% current efficiencies. And sometimes you can do that. The big advantage of the electrogravimetric methods is that you don't have to have 100% current efficiency. All you have to do is ensure that only the material that you're interested in plates out on that material. Okay. That's an example. This is an example of some stuff we use in our lab sometimes. Trichloroacetic acid in the acid solution can be reduced to the dichloroacetic acid plus a chloride ion, and it actually works out that we can do this reaction even in other forms, the dichloro and the monochloro, which have a different reduction potentials. You can use the same idea of coulometry not only to determine the amount of material that's initially present, but more likely people would often use this to determine the number of electrons in the system. Given with an initial starting amount of material that you can determine, you can actually determine the number of electrons that you've actually added to the system. to get the dichloroacetic acid. And that's often something that's not obvious from the system, so that's something people often want to know. Problem also that coulometry addresses is that, unlike voltammetry, if you remember, in voltammetry, particularly for diffusion type processes, we need to know the diffusion coefficient all the time. And the diffusion coefficient is actually something that's not always tabulated in books. It's not always available for a particular system. And so the coulometric methods don't have to don't have a diffusion coefficient in it, so we don't have to worry about that. So using a combination of coulometry and voltammetry, we can also often tease out the relationship between the number of electrons and the diffusion coefficient and concentration. So if we use two methods, we can actually get usually the three variables. So if we have an unknown species, we don't know the diffusion coefficient, don't know the number of electrons, don't know the concentration, we have to use a combination of methods to get C, D, and N, which are often not available. Now, the one problem with coulometry and voltammetry, too, that can be sometimes a disconnect between the two processes is that coulometry and voltammetry often occur at vastly different time scales. So one thing that can happen is that, well, we want to use coulometry to determine N and use voltammetry to determine D. What can happen is situations like this, where you have an electron going in to reduce something, but R undergoes some follow-up chemical reaction, which may or may not be electroactive. All right? So if Q, or if Q can be reduced, which is often the case in some organic systems, or if Z can be further reduced sometimes, it can also be the case, that will throw off our system, because now we'll have an additional reaction occurring in the time scale of the reaction. It only really is a problem if K is fast enough, is faster than the time scale of the experiment. Now in voltammetry, often we can do a reaction within a few seconds, so K would have to be pretty rapid. But in coulometry, the reaction may occur over a period of an hour or so. So the two time scales being so different, the effect of, say, a reaction can often creep in. And so one of the things you have to be real careful about in these methods is to avoid or know in ahead of time whether or not you're going to have side reactions that will interfere. Now, voltammetry is good to eliminate these side reactions. Coulometry, you have to live with it, basically. So there's always some sort of compromise you have to deal with. Let's stop here for a break, and then we'll continue with the rest of the chapter.